Hello guys. So today we will study the convection topic. This is the very important topic of the heat transfer. So in any convection heat transfer problem, it is required to obtain the convection heat transfer coefficient H for a given boundary condition prevailing between body and fluid, and hence to obtain the convection heat transfer rate between them from Newton's law of cooling. That is, what is Newton's law of cooling? That is the heat transfer Q convection. Q convection is equal to H delta T. Actually, this is the heat flux means heat transfer per unit area. So, capital Q we can write as H A delta T. So, for that, in any medium, if we want to find out what is the heat transfer through convection, so we have to find out the H, heat transfer coefficient. Heat transfer coefficient in that medium. Okay. So, if I'll talk about convection, so there are two types of convection. First is forced convection heat transfer, and second is natural or free convection heat transfer. Fine. Forced convection can be of two types. First is flow over flat plate, and second is flow through pipes. Flow through pipes, and in free convection. So in this type of convection, no velocity evident, but the flow occurs naturally due to the buoyancy forces arising out of density changes of fluid because of its temperature change. So we can see some examples if I talk about the if I talk about the flat plates. Let's see, we have a flat plate, vertical flat plate. So due to the natural convection, the profile will be like this. So this will be the velocity profile through this plate. So if I talk about like P is equal to rho RT, or P upon rho is equal to RT. So as the temperature is increasing, density get decreased. This is the direct relation. If I talk about the flow over flat plate, let's say we have a flat plate and the flow is going over it, like let's say V infinity. So the if I talk about the boundary, then there will be a boundary formation. So what is this boundary about? This boundary is actually denoting the denoting that at how much distance, let's say we have a distance of x, that at how much distance of x the shear stresses are dominating. So at this location, if we go till this point, let's say delta, so till this delta distance, the shear stresses are dominating. So if we draw the velocity profile from the flat plate to this boundary, so we'll get a parabola like velocity profile. And at the boundary, this velocity profile will approach approximately to 0.99 v infinity. Fine. If we want to find out the gradient of this velocity profile, then that will be del v upon del x, because v is in y direction and u is in x direction. Okay, this is why this is the flow over flat plate. But here one thing we have to keep in mind, that here v is a function of x and y both, because v is changing with respect to x and as well as with respect to y. If I talk about the flow through pipes, let's say we have a pipe. Okay, let's say we have a pipe So let's say we have taken a cross section here. Okay. So the velocity profile will be again will be like parabolic, and the velocity here will be function of radius. This is the radius, and if we want to find out the mass flow through it, that will be rho pi r square v mean kilogram per second. From this equation we can find out the velocity. So finally, if I talk about the force, first I will talk about the force convection heat transfer. Force convection heat transfer, if I talk about, so in any force convection heat transfer, the heat transfer coefficient will depend on many factors: the velocity of the flow, uh, the characteristic diameter, or anything else. Let's see, if we have a pipe, then that characteristic dimension will be the diameter. Then depends on the density, the dynamic viscosity, with Cp and uh, conduction heat transfer coefficient. Okay, and these three terms, mu, Cp, and K, these are called thermophysical properties of fluid. This is very important. These three properties, mu, Cp, K, is called thermophysical properties of fluid. We'll further understand in proceeding slides. So here the v is the velocity of the fluid and d is the characteristic dimension of the body. Okay. So if we want to find out the what are the characteristic dimension, then let's say for the flat plate, the dimension will be its length, d will be its length. For the case of the pipe, the dimension d will be its diameter. For the case of, let's say we have a flow through non-circular ducts, let's say we have a square or rectangular duct we have, so that let's say it's A and B is the dimensions, so its characteristic dimension D will be 4A, uh, it is 4A upon P, that is area, means 4AB upon 2A plus B is the dimension, characteristic dimension. And for the case of flow over across a cylinder, let's say we have a cylinder like this and flow is passing through over it. So what is the characteristic dimension? Characteristic dimension D will be again the diameter of the cylinder. And let's say we have a flow over a sphere. If there is a flow over the sphere, then the characteristic dimension will be again the dia of sphere. And so if we want to find out that H by applying the Buckingham pi theorem, so from Buckingham pi theorem of dimension analysis, which states that if there are total n number of variables in any function relationship, both dependent and independent, and if all the variables put together contain n number of fundamental dimensions, then the functional relationship among the variables can be expressed in terms of n minus 1, n minus m number of dimensionless pi terms. Right? So we can write here from Buckingham pi theorem, here, because the total terms, that is h, is dependent on what? Velocity, dimension, rho, mu, cp, k. 1, 2, 3, 4, 5, 6, and 7. N is equal to 7, 7 number of variables. And what is n? The fundamental variables, that is m, l, t, and theta. Theta is the temperature, t is the time. That n is equal to 4. So the pi times will be is equal to n minus m, that is 7 minus 4 is equal to 3. So Total three pi terms will be there. If we want to find out the first pi term, that will be the function of pi 2 and pi 3. So, uh, so these dimensionless pi terms obtained from dimensional analysis technique can be directly equated between model and prototype if there is a complete similarity is existing between them. As we know that we can apply the dimensionless formulas in between the model and prototype. Okay, so I mean by applying this rule and finding out the different uh, dimensions, so we are getting that the pi 1 terms we will get hd upon k, that is called the Nusselt number. The pi 2 term will get vd rho by mu, that is called Reynolds number. The pi 3 terms mu cp upon k, that is called Prandtl number. So from these relationships, we can say that what we are getting that we can say that Nusselt number is a function of Reynolds number and Prandtl number. We can say, okay. So we'll try to understand these physical significance of dimensional numbers in force convection and transfer one by one. First, let's say try to understand Reynolds number. What is Reynolds number? So as we have got that Reynolds number is equal to rho v d by mu. So what is showing? So Reynolds number is defined as the ratio between the inertia force and the viscous forces to which a flowing fluid is subjected to. Okay, so basically, Reynolds number shows the inertia force divided by the viscous force. It is showing the respective inertia force and viscous force ratio. Okay. One more thing we can manipulate here, that we know that kinematic viscosity nu is equal to dynamic viscosity by density. So we can uh, change it here, that v d by nu, because we'll divide rho from mu. Okay, so from this manipulations, we can say that a fluid having more viscosity would require more amount of energy to be supplied to the fluid to maintain the flow in a given pipe diameter. And with a given flow velocity, because such fluid will suffer greater friction resistance against its flow. So from the Reynolds number, we can say that if Reynolds number is much greater than 1, it means that its inertia force is dominating. Its inertia force is dominating. It means that it can easily flow. It has not much resistance in the flow. It can easily flow because its Reynolds number is more. It means that its inertia force is dominating to the viscous force. Let's say if I talk about the if we want to find out the uh, dynamic viscosity of air. So it is the 18.0 into 10 to the power minus 6 Pascal second. So is or we can say that it is 18 micropascal second. So very less viscosity in the air. So basically for the air, Reynolds number is more because there is very less viscous effect of the air. So Reynolds number is the criterion to tell whether a given fluid is laminar or turbulent. We can also decide it.